Let's now look at our third example. In this example, we have a force of 8 pounds, and this force is required to hold a spring stretched 2 inches beyond its natural length. We want to find how much work is done in stretching the spring from its natural length to 8 inches beyond its natural length. The force required to hold the spring stretched is given by Hooke's law, and that's F is equal to K times X, where K is equal to our spring constant. Because our force is a function of X, the work is going to be equal to the integral from A to B of our force, which is our f of x, times dx. To evaluate this integral, we need to find A, B, and K. Let's find K first. K can be found by the equation F is equal to K times X. Since a force of 8 pounds is required to hold a spring stretched 2 inches beyond its natural length, we can let our force be equal to 8 pounds. And then we have our K, and then X is going to be 2 inches. K then is equal to 8 pounds, all divided by 2 inches. The standard units for work is foot-pounds, so we need to change our inches to feet. So we're just going to multiply by 12. And we get 8 times 6, which is 48. And our units then are pounds per foot. Now let's find A and B. We need to find the work done in stretching the spring from its natural length to 8 inches beyond its natural length. When the spring is at its natural length, it's not stretched at all, so A is going to be equal to 0, and then B is the length that the spring is stretched, and it is going to be equal to 8 inches. We also need to convert this to feet. So we are going to divide this by 12. 8 divided by 12 is 2/3. So B is 2/3 feet. Now we can go ahead and evaluate our integral. Our work is the integral from 0 to 2/3 of our force F, which is K, which looking back up here, is equal to 48. So we have 48 times x dx. This is equal to 48 x squared divided by 2, evaluated from 0 to 2/3. This is 24x squared, again evaluated from 0 to 2/3. If we substitute in that x is 2/3, we get 24 times 2/3 squared, and then we're going to subtract off 0 for our lower limit. This gives us 24 times 4 divided by 9. We can divide 3 into both 9 and 24. So this gives us 32 divided by 3, and now we need units. Our force was in terms of pounds, and our distance is in terms of feet, so our units are foot-pounds. If we want to know what this is in terms of a number, we can say that our work is approximately equal to 10.667 foot-pounds. Now let's look at our last example. This is another spring example, but it's different than the one that we just did because it involves compression. In this problem, we're told that a spring has a natural length of 60 centimeters. A 45 Newton force is applied to keep the spring compressed by 15 centimeters. We want to find how much work is required to compress the spring to a total length of 30 centimeters. Similar to our previous problem, the work required to compress the spring is equal to W, and it's the integral from a to b of f of x dx, where f of x is equal to kx, which is found from Hooke's law. To evaluate our integral, we need to find k, a, and b. Let's start with k. We are told that a 45 Newton force is required to keep the spring compressed by 15 centimeters. So we can let our force F be equal to 45 newtons, and it's equal to K times how far the spring is compressed by this force, and that is equal to 15 centimeters. This gives us that K is equal to 45 newtons divided by 15 centimeters. We need to change to the standard units of meters, so we're going to multiply by 100. And we get a value of 300 newtons divided by meters. I'm going to highlight that because we'll need that in a minute. Now let's find A and B. Initially, the spring is not compressed, so we're going to let A be equal to 0, and then B is the length the spring is compressed, and that is going to be 60 centimeters minus 30 centimeters, because its natural length is 60 and it gets compressed to 30. So B is equal to 30 centimeters, and we need to change this to meters, so we are going to divide by 100. And we get 0.3 meters for B. Now let's go ahead and evaluate our integral. Our work is the integral from 0 to 0.3 of k times x. K is 300, so we have 300x dx. This is equal to 300 x squared divided by 2, and x goes from 0 to 0.3. We then have 150 times 0.3 squared, and this is equal to 13.5, and our units are going to be newtons times meters, and we usually write that in terms of joules, so we get an answer of 13.5 joules. And that's the amount of work that is required to compress our spring from its natural length of 60 centimeters to 30 centimeters.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.